Welcome to the video lecture for your first bada application. In this lecture, we're going to explain how to develop your first applications using the bada SDK along with bada namespaces and APIs. We'll cover all the topics that will help you to create your first bada application. We'll discuss the bada API overview in detail, the bada namespaces, the access and privilege levels of APIs and modules, the application framework, how to use the template code, how to create the UI, as well as more details on the app namespace with some examples for your understanding. We'll start with the bada API overview. In the bada API overview, we'll discuss the bada namespaces and privilege levels in more detail. Here is the bada namespace list, which is displayed in the bada SDK help content. You can select or explore each namespace if you want to see more content in detail. This will take you to the overview and the individual APIs for the selected namespaces. For example, we've selected the location namespace and we can see the corresponding header file, more details of the location namespace, and the descriptions of the location module. Also, you'll be able to find some sample API usage and API descriptions for the selected namespace. This will help you to create your applications more easily. An API that handles platform and user-sensitive data has privacy, security, and stability implications. To address this, the APIs are divided into groups with different privilege levels. To be able to use privileged APIs, an application must have the corresponding privilege level and groups assigned to the application profile on the bada developer site. We have three categories of API access levels, i.e., for some APIs, users or developers do not require any privilege levels. Then, there are some APIs that are usable by all bada developer members, and some are only usable by Samsung developer partners. The privilege level defines the developer membership level required to have access to the particular API and must be declared in the manifest file of an application that uses this method. The privilege group means its predefined collection of privileged APIs that can be assigned to the application to allow it to call privileged APIs. It's very simple and easy to know the privilege and group of access for the particular API. Here in this example, we have the OSP, App, App Manager, Launch Application API, where you can check the privilege levels and corresponding group. This API has the System privilege level and comes under the App Service group. You can use the corresponding APIs which are required for your applications. We have now had a look at the bada namespaces and privilege levels and are gearing up to learn more about how to create a bada application. We'll now learn more about the application framework. To create your first bada application, you need to know about the application framework, the application model, the application life cycle, the template code that gets created while creating the project using the wizard, adding a user interface, event handling, and the OSP app namespace. The application lifecycle diagram explains the basic lifecycle of a bada application, including launching and terminating an application and the perspective shifts between the background and the foreground. Once an application is launched, it enters the initialization stage, during which it will show and then hide the splash screen. After the initialization is over, it will change to the running state where it moves to the foreground. After running the application, the terminating process is called to close the application. If any other apps come to the foreground or any other system pop-up messages appear, the current foreground application will be moved to the background. Finally, if you want to close the application, you need to press the End key or call the termination process to close your application. At the time of termination, it will release all the resources which were used by the application. Applications are visible when they are in the foreground. When an application is first launched, or when it's brought to the foreground from the background, the onForeground method is called. An application is brought to the foreground from the background when the running application is selected from the task manager, or the application icon is selected from the main menu. Applications are not visible when they are in the background. While multitasking is enabled, pressing the Home key makes the application move to the background. We're going to discuss the callbacks mentioned here in the following slides. To start your application, you need to know the files and the main function. The OSP main function is the entry point for any application. Once you complete creating the project, there will be a file called xxxxentry.cpp, where xxxx is your application name. Your OSP main function will be inside this file. This is the starting point for the application. Then, the framework will initialize your application and all your resources, and the registry data will be loaded. Then, the OSP main function will invoke the onAppInitializing method, where you need to implement your initialization code. If the OSP app application onAppInitializing event handler returns false, the application state changes to terminating and exits. If the event handler returns true, the application enters the running state and can instantiate its resources, such as the UI controls and state. The visibility of bada applications depends on two perspectives, the foreground and the background. When launched, an application can be switched between the two perspectives, foreground and background, to control its UI visibility. The applications will be invisible or partially hidden by another window, such as a pop-up message, when they are in the background. In bada API version 2.0 or later, you can use the OSP app application get app UI state method to get the UI visibility state of the application. And an application moves to the background when the Home key is pressed. Also, when other windows, such as windows for incoming calls and alarm pop-ups, they cause the focus to be moved to the new window, and the running application moves to the background. It's best practice to stop drawing when the application moves to the background. We can stop any graphics processing, such as a 3D or animation item, as they will not be displayed. Also, we can release unnecessary resources and stop media processing, haptic effects, sensor manipulations, and location updates. However, for a partially visible application, it's recommended to hold or pause its active tasks or resources instead of terminating or releasing them. Now, let's discuss the foreground perspective. The applications are visible when they're in the foreground. When an application is first launched, its splash image is displayed, and then the onForeground method is called immediately after the splash image has disappeared. An application moves to the foreground when the application is selected from the Task Manager list, or when the application icon in the main menu is pressed, when the application is in the background, or when an application is to be launched while it's running in the background, or a system pop-up such as an incoming call, a notification such as an SMS, or a low battery warning pop-up disappears. If you stop drawing when the application moved to the background, remember to resume drawing when the application moves to the foreground, if required. You can resume the graphics processing such as a 3D or animation item as the application now has the focus. Also, resume the operations that stopped when the application last moved to the background. You can also refresh any screen element by calling the onForeground method when the application is present in the foreground. An application is closed either by a user action or when the system forces it to shut down. User actions can be any of the following. When the bada application itself calls the application terminate method, the application is terminated. When the application is running in the foreground and the device user presses the end key, the application is terminated. In non-multitasking mode, a user launches another bada application and the old application is terminated. In non-multitasking mode, the system forces the application to shut down when the memory or battery power is extremely low. The onApp terminating class is called when an application's state changes from running to terminating. All the activities involved in terminating the application, including saving the application's states, should be done in this method. After this method, the application code cannot be implemented. The application is subsequently destroyed. In this method, you can free all resources, close the network connections, and save the current settings. The important point to be noted is that you don't need to access the UI in this method. With the potential for multiple applications to be running in the background at the same time, low memory situations are much more common. Now, let's see what happens in multitasking mode in this case. For these API versions, when the system is running low on memory, the system begins to terminate the applications one by one until sufficient memory is available. The applications are terminated in the order the user last placed them in the background. This means that the application which has been in the background the longest, since last being in the foreground, is terminated first. The system does not alert the user about the forced terminations until the memory status is back to normal. When the memory levels are extremely low, the system can terminate an application and remove it from the memory without alerting the user or calling the onApp terminating event handler. In C++ and Flash applications, you can avoid situations in which important application data is lost due to this kind of termination by saving the application state or context to the application registry, or storage by implementing the iApp checkpoint event listener interface. Its onApp checkpointing event handler is called in low memory situations in which a background application is likely to be terminated. Similar event handlers are also available for web applications. Now, let's move on to discuss the application class. This is the base class of a bada application. An application must inherit from this class when it's created. This class provides the basic features necessary to define the application. In order to run the application in bada, the application class must declare and define a static factory method that creates an instance of the application class. Since the code for the method is generated automatically by the IDE, it's recommended that the code is not manipulated manually. In this inherited class, you need to implement the methods for the state transition and the event handlers for system events and user events. Also, the application class provides methods to access the name and version, to get the app registry and resources, to get the main UI frame, and the current state of the application. I'll explain these functions in the coming slides. Now, let's check the application states with the corresponding event handlers in detail. All bada applications have 4 states: initializing, running, terminating, and terminated. First, let's look at the initializing state. The application framework initializes the application and creates the application's frame. The user interface is constructed and the application data saved on the previous run is restored. The onApp initializing event handler supports this state, and if it returns false, the application state changes to terminating and exits. If the event handler returns true, the application enters the running state and can instantiate its resources, such as the UI controls and the state. In the running state, the application can switch between the background and the foreground. The on-foreground and on-background event handlers support these transitions. In the terminating state, the application removes its own resources and saves its preferences. This can be done in the on-app terminating event handler. The web application does not need to remove its own resources, since the web framework does it automatically. And in the terminated state, the application framework removes the application from memory. Since we've already discussed the event handlers in the previous slides, let's move on to the other event handlers and methods of this class. Here, we'll see how the application can handle system events and user events. The system events that application needs to handle are the battery event and the memory event. Applications that use multimedia resources, such as the camera and media player, need to check the battery level in the on-battery level changed event handler. This event handler is called when the battery level changes. It's recommended that applications that consume more battery power should be terminated if the battery level is OSP, System, Battery, Critical. When the system detects that the system-wide memory or application heap is insufficient to continue running the application, the on-low memory event handler is called. To address the low memory state, the application can free unused memory from the heap in this event handler. To handle user events, we have the onUserEventReceivedN event handler. This event handler is called asynchronously when the user event is sent by the sendUserEvent method. As discussed, the application class has APIs to send user events, to control the application lifecycle, and to query different application information. Let's dig into these APIs. To send a user event to the application itself, we can use the sendUserEvent method. The parameters, the request ID and argument format for the user event can be defined as per the requirement. The point to be noted here is that we cannot send user events to other applications. If you want to terminate the application at some point, you can use the terminate method. To query different information related to the application, we can use the following APIs. To access the application mainframe, you can use the getAppFrame API. You can get the application ID using the getAppID API. The getAppName API gets the name of the application. The app registry and app resources can be accessed using the getAppRegistry and getAppResource methods. The getAppState API gets the current state of the application, and the getAppUIState API gets the UI state of the application. To get the version string of the application, you can use the getAppVersion method. You can use the getInstance static method to get the application's instance pointer. Now that we've discussed what we need to know before creating an application, let's move on to create our first application and understand the skeleton code in the template files. The bada SDK is packaged with its own IDE based on Eclipse. You can use this IDE to create your project, add or edit code, compile, and run it. Let's walk through the steps of the application wizard. In the IDE, select File, New, bada C++, Flash Application Project. Give a name to the project and select bada Form Based Application Template as we're about to create a simple application. Click Next. As we're focusing on creating our simple app, let's skip this step and leave the Default Manifest File checkbox checked. Click Next. Here, we can select the resolution of the device on which we are planning to deploy our application. Click Next. In this step, we can define the basic properties of our project. Example, name. By default, it will have the name which we set in the first step. Click Next. Here, we can set the name of the form and the base class. Then, click Next. This is the last step, and we can make sure that our application has auto-scaling enabled and set the base resolution. Auto-scaling will help to make sure that the correct resources are chosen for each resolution. To learn more about the SDK IDE, you can watch the lecture video on development environment. The base class and related files will be created when the project creation is completed. Now, let's look at these files and the generated template code. In our project, we're first going to walk through the hello world.h file. Here's the declaration of your base class, which inherits from OSP app application and OSP system iScreen event listener. Since the application is a subclass of OSP app application, we must override the implementation of the state transition and the event handling methods. Further into this header file, we can see these event handler declarations. These are the event handlers inherited from OSP app application and the iScreen event listener. We discussed almost all of these methods in the previous sections. OnScreen on and OnScreen off are event handlers of iScreen event listener. We've now seen the header file declarations. Now, let's walk through the default implementation of the event handlers available in the template code. You'll find the default implementation of the onAppInitializing method in the helloworld.cpp file, which contains the implementation of your base class. This method will be the correct place to initialize something in your application, so you can start implementing the code accordingly. Usually this method will by default contain the initialization code of the UI form, which is hello world form here, and adding the UI form to the UI frame and also bringing the current form to the front. You can also add reading the registry and allocating the required memory for your application, etc. in this method. Next is the onAppTerminating event handler, which has two input parameters, app registry and forced termination. Where the app registry is the instance that manages the application's states, and forced termination is set to true if the application is terminated by false interruptions. In this method, you need to free the application resources, clean the memory, disconnect any network connections, change the registry values, and save the values into the registry. Now, let's look at the implementation of the onBackground and onForeground event handlers. In the onBackground method, we need to stop if there are any ongoing continuous processes, including animations, media playing, etc. And in the onForeground method, we can resume the stopped processes. Next, we're going to check the system event handlers. As discussed earlier, the onLowMemory method is called when the system detects that the system-wide memory or application heap is insufficient to continue running the application. Resources that are not currently in use can be released in this method. If onBatteryLevelChanged is true and the battery level is empty, it's recommended to terminate the application. If the battery level is critical, stop using the multimedia features since they are not guaranteed to function properly at this battery level. On-screen on is called when the screen turns off. Unless there is a strong reason to do otherwise, you are recommended to release resources such as 3D, media, and sensors to allow the device to enter sleep mode to save battery power. Invoking a lengthy asynchronous method within this listener method can be risky because it's not guaranteed to invoke a callback before the device enters sleep mode. Similarly, you should not perform lengthy operations in this listener method. All operations must be quick ones. On-screen on is called when the screen turns on. We can get the released resources or resume the operations that were paused or stopped in the on-screen off method. I hope you've enjoyed this session on application template code. Now, it's time for us to move on to the next topic. We'll discuss and understand more about the UI created by default and check how we can modify it. After creating the test application project using the bada SDK, you can browse the following path: /res /screen size normal / of your application and open the IDF_form through the UI Builder. This will be the exact representation of your form, which you can see displayed on the emulator or device. By clicking on the OK button, you can see the properties of the button and modify them. You can see that the OK button has the ID property IDC_button_OK. At this point, if you want to, you can add more controls to the form. Now, let's try to understand the basics of a form. A form is a full-screen control that you can use to display an indicator area, header, footer, and other control areas on the screen. The form is the only instance which can be present as a child on the frame control. Also, it has several features, such as grouping controls, UI orientation management, page switching, and custom drawings. While starting the form, it will load the resource file which is specified by a particular ID. While initializing, it will connect subcontrols to the member variables and assign them to the corresponding listeners. At the time of termination, it will free all system resources. You can check the sample code which is using the form APIs. In the form1.cpp file, we have the initialize function. It has the code to construct and load the IDF_form1 file. We can set the class properties and create the subcontrols here. Form1 also has an action listener to handle button events. As with other UI controls that are derived from the OSP UI control class, when an instance of a form is added to a frame, the onInitializing method is called. Similarly, when the form is removed from the frame, the onTerminating method is executed. An application can override these methods to provide its own initialization and termination logic. If the form displays a pop-up window, the form must deallocate the window before being terminated. The current form must not be deleted from the OSP UI controls message box class, which uses a modal loop with the show and wait method. The framework will invoke the onInitializing method of the form. Then, we need to do the form-specific initialization tasks. The following are the specific initialization tasks which we need to do at the time of initialization. Identify the subcontrols which is made in UI Builder to make the setup. Then, we need to create the additional subcontrols and attach them to the form. We need also to add the listeners to the controls and if we have any other initialization tasks. This is the default on-initializing code available in the form1.cpp file. As we saw earlier, IDC _button _OK is the ID of the OK button in Form 1. We can see that the getControl method with the ID, here IDC _button _OK, is used to get the control, i.e. the OK button. If the button instance is available, the action ID is set and the action event listener is added. A listener is an interface with specific methods to handle events. The framework processes low-level events and passes them on to the listeners. Controls and other classes may have listeners to receive various notification events. iAction Event Listener is an interface to handle control-specific actions, such as buttons being pressed. It has the event handler onActionPerformed associated with it. Now, let's check the onActionPerformed method in our template code. The action ID was set as ID _button _OK in onInitializing. So, the code here is implemented as checking the action ID, and if it is ID _button _OK, the message the OK button is clicked is printed in the log. If you compile and run the code, you can see the log as shown in the output window. Application termination tasks are handled in the onApp terminating event handler. When the event handler is called, the application frees its resources and terminates. The allocated UI controls, such as the frame, form, and their child controls, are released before the onApp terminating event handler is called. These UI controls are not accessible from within the onApp terminating event handler. If you need to access these UI controls before the onApp terminating event handler is called in the terminating state, use the iframe event listener onFrame terminating event handler. Let's experiment by modifying the template code to change the icon and splash screen, adding code to respond to user events, and modifying the UI at runtime. You can replace your icons in the following ways. Rename your icon name to the default icon name, or change the project icon name and add your icon to the project using the Project Explorer. This is the same way you can change the splash screen. Also, there's an important note that to sell your app in Samsung Apps, you must use a custom icon and splash screen. Similarly, you can also change the other icons. You can find more details on icons and how to handle the icons in various resolutions from the help contents. If you want to modify the UI, double-click on the IDF_form, which is normally available in /res/screen size-normal /IDF_form in the Project Explorer and check the properties. Here, we can change the label on the button by clicking the OK button and double-clicking in the Properties window. Similarly, you can add more controls to the form by dragging and dropping them from the toolbox. Also, by double-clicking on the newly created controls, you get options to add the required or possible listeners. For the action listener, you get the option to add an action ID here. Now, let's check how we can identify the newly added button and label. In your form's header file, you'll find some declarations, ID _button _OK, and its value, 101. Also, you'll find the new ID for the new button as ID underscore button underscore test equals 102 and P label as the pointer to the new label. The code given here explains how to identify and set up the new controls in your application. After loading your UI file, you need to implement the label, which you have added or newly declared in your header file. You need to get the control of the label, and you also need to set an action for it. Here is the implementation. As we've seen in the case of the OK button, we can get the pointer to the label by using the getControl method to pass the label ID. If we added the action listener and action ID for the button, the code corresponding to it will be automatically generated in your source file as shown. Next, let's look at how to respond to user events. When onActionPerformed is called, we'll check the ID and try to perform something. Also, experiment how to modify the UI at runtime by changing the text on a label and forcing a form redraw. Here's how we can do this. I've used the new button, Test, to do this experiment. In onActionPerformed, I'm checking whether the test button was pressed by checking the action ID against ID underscore button underscore test. If this is satisfied, I use the pointer to the label to set the label text to setText L. Oh yeah, by using the setText API. Then, by calling the requestRedraw API, I'm redrawing the form to be able to see the changed label. We've now had an overview of the bada APIs, created a simple application, looked at the application framework, the template code, and how to use and add a form and UI in detail. We'll now look at the OSP app module in more detail. This will just be an introduction to these classes, and you need to dig into the help contents to get a more detailed idea. The OSP app registry class manages an application's preferences. It provides the access to an application's registry. It creates the app registry file and is used to store the application settings for the application. You can access the registry file using the onApp initializing method with appreg as a parameter. Initialize the application by retrieving the application data from app registry with the get method. Initializing resources, including the UI construction, and restoring the latest states is generally handled within the onApp initializing method. Save the application data in app registry with the set and save methods. Data saving is generally handled within the onApp terminating method, which is called when the application is terminated. Here's the typical usage of the registry. In this example, I get the delay value from the app registry during initialization, and, if successful, I use the value in my application. And in the onTerminating method, I save the delay value to the app registry so that it can be used in the next run. Next is the App Resource class. The App Resource class provides convenient methods to load application resources at runtime. Using the App Resource getString class, a caller can get localized string resources for internalization. And here are the string resources in a multi-locale format: eng-gb.xml, fra-fr.xml, kor-kr.xml. Also, it gets the string from the specified resource ID. You can use string resources in your application to handle and display localized strings. the IDE generates language-specific XML files with the language and country code, such as eng-gb.xml, from the string tables to the res folder of the application project. The OSP app resource class of the app namespace handles localized string resources based on the preferred display language defined in the device settings. The app control method is a standard mechanism using specific operations exported by other applications, which is used to launch applications with an operation and data. Application controls can supply an operation and some data and get back results. Each application control can also have information associated with a URI scheme and a MIME type. The app control category determines the arguments that are sent and retrieved between the calling application and the application control. Using the app control, we can call a base application and perform the required job. Here are some useful base applications IDs. App control _audio will launch the audio app. App control _browser will launch the native browser. The allowed operations in the app controls are add, capture, edit, pick, etc., and can be used with the relevant app controls. Here's an example of making an emergency call using an app control. Prepare the calling method and number, get the dialer control using the static find app control n method, and start the dialer base app by using the start method. Once you're done with the controls, don't forget to delete the resources. This is the overall summary of what we've covered in this lecture. I hope you've enjoyed this lecture. Thanks a lot for listening.